Okay, back for one more example of the goodness of fit test. We're still dealing with the chi-square distribution, and we did one example of goodness of fit in my last video, and it was a uniform distribution. Okay? We looked at the colors of a roulette wheel, and the key here was each one had an equal chance of getting hit. So when we wrote out a null and alternative, or null, the distribution of colors is uniform. What we were saying was the distribution between the red, the black, and the green, how they were spread out, how they were given out, was equal to each other. We found that obviously, even just by looking at it real quick, we thought green was going to be not equal to the other ones, and we ended up rejecting the null because of that. This is going to be slightly different, this example, because this next example is not going to be uniform. We're not going to have an equal chance for each one. Joe Betts thinks that the closer a horse is to the inside of the track when he starts a race, the better chance he has of winning. Below, he made a list of chances the horses have of winning depending on where they start. Test Joe's claims at 99%. So here we have position 1 being close to the inside down to position 8. And we have all the percentages. This is what Joe's claiming the proportion is. 30% of the chance, horse 1's going to win. For horse number 4, 13% chance. So this is what Joe's thought. This is the claim that we're testing. And here are our observed values here. 50, 42, 41, so we have our data collected. Okay? The null and alternative are similar. They're going to be statements again, but this time they're not uniform. Since our categories are not equal to each other, our null's going to read, the population fits the assumed distribution. We are assuming Joe's percentages are correct as our null, so it would be that position 1 is equal to 30%, equal to 15%, equal to 14%. So again, the null is staying with that equal. Okay? And our alternative, at least 1 is incorrect. Little harder for us to tell this time. Looking at these numbers, the roulette example, we could see easily the green didn't fit. This one, we're going to have to see what happens with it. Okay? Because we don't know which one, and there might not be 1. There might not be evidence that 1 is incorrect. Okay? Work is very similar. We have our null and alternative. Degrees of freedom is n-1. This time there are 8 categories. So 8 minus 1 is 7 for our degrees of freedom. Go to our chart. We're at 99%. Degrees of freedom is 7. And I have, quickly draw it here, skewed to the right. And I have it at 18.475. Okay, so there's our critical value. Right, reject and fail to reject. Okay, so there's our curve there. And now we're going to go through the same work. Finding the expected values and then calculating our test statistics. All that is the same as before. Okay, so finding our expected values this time is a little different. Okay, the expected values are going to be a little different. So we have expected. This time, we can't just add the observed values up and divide by 8. They're not equal. If they were equal, we could do that. But since position 1 is supposed to have 30%, position 8 is only supposed to have 5%, we're going to have to change this up a little bit. We still have to add them up. We still need our total. So if you add these up, okay, you should have a total of, I have it at 235. And now what you need to do is take each one of those percentages and multiply it by our total. That's going to be our expected value for each one of these then. So you would take the 235, multiply it by 30%. 235, multiply it by 15%. So if I start doing that, 235 times 0.3, that ends up being my 70.5. Okay. For the 42, that's the position 2 is 15, so that'd be 235 times 0.15. That ends up being 35.25. Okay, so I'm going to quickly get this done. Okay, you should do it yourself, and we'll come back together. Okay, so there are all our expected values: 70.5, 35.25, 32.9, 30.55, 18.8, 18.8, 16.45, 11.75. And I did have to move our curve over there, kind of put it in a bad position to start with. Now to find our test statistics is exactly the same as we did before. Okay, to abbreviate it, it should be our observed O minus our expected squared divided by expected. So it's the same formula as before. You're going to do that for each one and then sum all them up. Our summation sign is sum all them up. Okay, so I'm just going to do one or two of them. You should have 50 for the first one minus 70.5 squared divided by 70.5. Okay, so that's what you're going to be doing for each one. 50, our observed, minus our expected 70.5 squared divided by the 70.5. Our next one would be 42 minus 35.25 squared divided by 35.25. And you're going to keep doing all that for all of our test stats. Okay? So I'm going to real quick write them on the board and add them up and see what we get. Okay, so there's all my test stats around to 3 decimal places. I have 5.961, 1.293, 1.994, 1.817, 0.077, 1.226, 0.365, and 1.537. If you didn't think back to our last example, the test stat we had was very big. It was a total of, I think, about 124 was our test statistic. All those numbers were very far from each other. We went from 141, our expected was 100. Our observed was 150, our expected was 100. They were far away from each other. This time these values are not exactly right next to each other. 50 to 70.5, 42 to 35.25. Down here they're fairly close. 14 to 16.45, 14 to 18.8. So some of them are very close to each other. If you were to add all those up, you should get about 14.27 would be our test statistic. Label that as test stat. And just like before, we're going to look and see where it falls on the curve. This time, it's going to land somewhere on this side, which is our failed to reject. So we fail to reject the null. There's no evidence that at least one of them are incorrect. There's no evidence to say that any of his predictions, his percentages, are wrong. So we're just going to go with that. And maybe Joe has something going here and he's going to win more than he loses. Okay? So the most thing you need to point out here for this example compared to our other one is how we got our expected values. These expected values you need to multiply by the percentages. Find your total, multiply by the percentages. For the uniform one, we can add up and divide by our number of categories. So that you have to read through the problem and decide, is there a uniform distribution here, or is the distribution going to be different for each one of our categories?